Hi everybody, it's Cameron here, and today we're going to be looking at chemical changes, specifically reactivity series, displacement reactions, extracting metals, salts from metals, salts from insoluble bases, as well as neutralization and the pH scale. Okay, so let's start with what a reactivity series is. Okay, so most metals are in the form of ores. Okay, and this means that they are chemically bonded compounds. Okay, so it's going to be a metal bonded with another element. Okay, so many of these metals have been oxidized, usually, meaning that they have an oxygen bonded to them. So something like rusting, the creation of iron oxide. Okay, so a metal oxide is reduced to extract the metal, and we're going to go over exactly how that happens in the next slide. So what is a reactivity series? It's going to be a list of the reactivity of metals, okay, or a group of metals. Most reactive metals are going to be at the top and the least are going to be at the bottom. Now what this means is the metals are going to be ordered by looking at their reactions with water. Okay, so the more reactive it is, the faster it's going to react with water. Now sometimes some of these metals can be so unreactive that water will take too long. So what we have to do is instead react it with a dilute acid. And hydrogen gas is going to be released during this as the water molecules are split up. And the oxygen goes to your metal while hydrogen is given off. So one of the first ways we're going to look at it, how you're going to get metals from an oxidized state, is by reacting them with a more reactive metal. Okay, so let's have an example here. If we have something like magnesium and copper, okay, so ions in a solution of copper sulfate. So if we are trying to extract copper from this ore, this copper sulfate, okay, we can react it with something like magnesium, and magnesium being a more reactive metal, it's going to displace the copper in the copper sulfate, and it's going to become magnesium sulfate. Okay, so the copper is going to go from an ion being in that compound to being a solid, stable element, okay, which we can then take out through filtration usually, while the new aqueous solution is going to be magnesium sulfate. Okay, hope that makes sense. And so the magnesium is going to be oxidized as it has lost electrons to become an ion to react with sulfate, while copper is being reduced. It has gained electrons so that it can be a pure element in a solid form. And remember the acronym oil rig. Oxidation is loss, reduction is gain. Okay, so let's look at extracting metals. So a lot of the times when we have metals, we're going to be extracting it from the earth. Okay, it's going to be mixed in with the rock. We call this an ore. Okay, so some metals are more reactive than others and will be more integrated into the rock, while others that are unreactive, such as our gold and silver, will be these pure veins of metal, of gold or silver. Okay, it won't be as much contaminated as our other rocks, our other metals, okay, because it's less reactive. So when it comes to the metal extraction, it's going to depend on how easy it is to extract the ore. Some of them require intense processes, while others, it's very easy, okay. How much metal the ore contains, okay, as well as the changing demands for a particular metal. Okay, so in South Africa, for example, we used to mine a lot of gold out of our grounds, and we still do, but it used to be a lot, okay? Then we had these big mine dumps made. Go look at Johannesburg mine dumps if you're interested. And what happened was these mine dumps, where all the soil was taken out of the ground and made mountains, big mountains of these mine dump waste soil, okay? It wasn't beneficial for them to go through that soil at the time. Now what they are doing with higher advanced or more advanced technology, as well as an increased demand for gold, they are going through that mine dump again to extract the smallest amounts of gold that they can find, whereas previously it wasn't feasible for them to do that. Okay, so Less reactive metals can be extracted by adding either carbon or hydrogen. So we can see here metal oxide plus carbon will give us a metal plus carbon dioxide, okay, whereas tungsten oxide plus hydrogen would give us tungsten and water. So when we react it with a carbon, it's going to give it carbon dioxide. When we react with hydrogen, it's going to give us water. Okay, so the more reactive metals than carbon, we're going to use electrolysis to separate them. And remember, because it's an ionic compound, it has to be in an aqueous solution or it has to be melted. Okay, so salts from metals. So a salt is going to be when a metal reacts with an acid to form a salt. Okay, basically what happens is the metal is going to replace the hydrogen in our acid. Okay, and that means hydrogen gas is going to be given off. So this is going to be a redox reaction, okay, and it has to be that our metal is going to be above the hydrogen in reactivity. Okay, so it has to normally be a reactive metal, okay, because it has to displace the hydrogen in the acid. Okay, another way of making salts is by reacting acids and bases. So acids on the one side of the lower end of the pH scale, while bases are on the high end of the pH scale. If we put them together, they are going to neutralize each other around 7 pH. Okay. What's going to happen as well is a salt will form plus water. Now what happens is the acid is going to provide our negative ions, while our positive ions are going to come from the base. Okay. And it can come from a base, metal, or a carbonate. Okay, and see here, it's going to have no overall charge, and that means that it is neutral. That means this reaction is called neutralization. Okay, so let's talk about how we're going to make salts. Okay, so the first way we know with an acid and an alkali together, so neutralization. The next one is with an acid and a carbonate. Okay, both are going to make salts. And an example of which is your hydrochloric acid plus your sodium hydroxide is going to give us sodium chloride plus water. Okay, as we can see, the sodium is going to displace the hydrogen, okay, and we're going to get H2O from the hydroxide ions left behind by the alkali as well. Okay, so to collect a pure substance of these salts, what's going to happen is you're going to start by performing a titration. This is when we add acid to an alkali very slowly until the pH changes and becomes neutral. Okay. Once we know the amount of acid required to reach that titrate point, okay, we're going to do it again, but this time without the indicators so that it doesn't contaminate our crystals. And then we're going to have pure water and a salt, theoretically. And that's how we can then separate them. Okay. And then finally, the other one that we mentioned was an acid plus a carbonate. Okay, this is going to give us water, carbon dioxide, and a salt instead of just water. Okay, nice and easy. And then yes, to get a dry sample, you're going to do the same thing, but this time crystallized out of the solution by evaporating off the water and drying with a filter paper. So same thing, the carbon dioxide is a gas, so it will leave the solution and we won't have to worry about it contaminating anything. Okay, so a lot of writing, but don't worry, I'll just summarize it now. So when we're talking about neutralization in a pH scale, we said that on a pH scale, you're going to have your more acidic substances at the bottom half and your more basic or alkali substances at the top half. Okay, when we add these together, they can neutralize each other. As we can see, some examples of our bases are things like baking soda, ammonia solutions, soapy water, okay, and as we get closer to the center, we're going to see distilled water, neutral, okay. Urine is actually also pretty neutral, which is quite interesting, and as we go down, eventually we get to our own stomach acids, which are extremely acidic. That's how we are able to break down something like meat, okay. And so how we're going to know the pH of something? Well, we have some indicators, okay, something like pH paper, but they kind of give us a sort of not too accurate measurement. Okay, we have some pH indicators that are going to be able to give us a certain number of colors, okay, that we would then compare to a piece of paper that's given to us in the test kit, okay. But if we want an accurate number, then we're going a pH indicator, okay. It's going, or pH meter rather. This pH meter is a long tube with like a little glass ball on the end. And what's going to happen is you put that into your solution and it will give you the exact pH to the number, to the decimal point. Okay, whereas you can also use the pH indicator papers, but they're a bit less accurate. Okay, so when it comes to neutralization, it's pretty self-explanatory. As we've mentioned, if something is acidic, it's going to have a low pH. As we add an alkali, it's going to increase the pH until eventually it becomes neutral. Then if we carry on adding alkali, it's going to increase the pH more and become a basic solution. Okay, so acid plus an alkali is going to give us salt plus water. This is also going to be an exothermic reaction. It gives off heat. So an acid has to be in an aqueous solution, which means it has to react with water to show its properties. When it reacts with water, it's going to ionize. Okay, it's going to split up and you're going to have these free hydrogen ions floating around. This is what gives it its acidic properties, that all acids are going to have these free hydrogen ions moving around. Okay, a strong acid is going to be completely ionized in the aqueous solution, such as hydrochloric acid. Okay, whereas a weak acid is not going to completely ionize, and this is something like ethanoic acid, which we can see there still contains some hydrogens in the negative ion. Okay, so if all of these hydrogens were to come out, then it would be a strong acid, something like hydrogen chloride. Okay, and when it's a weak acid, it's usually going to be reversible, as we can see here. Okay, so this isn't just all theory, we can actually add numbers to this. Okay, when the concentration of hydrogen ions is high, okay, something like 0.1, okay, it's considered a strong acid with a pH of 1. Okay, but as our concentration of hydrogen ions decreases, the acid becomes weaker and the pH is going to get higher, closer to neutral and to alkali. Okay, this has been Chemical Changes. My name's Cameron and I'll see you in the next lesson.